Now we're going to talk about the properties of waves. The first thing we need to know that waves are a means of transferring energy or data or information without transferring actual matter or particles. So this is caused by vibrations or disturbances in a medium. So this vibration is transmitted, or we transmit the kinetic energy of the particles through the medium without transferring the particles themselves from one place to the other. We have many types of waves. A progressive wave means that there is a net transfer of energy from a starting point to an ending point. We have two types of waves that we call mechanical and electromagnetic waves. For a mechanical, there is vibration of particle or particles. And for electromagnetic waves, there is a variation of electric and magnetic fields or electromagnetic fields. So in a mechanical wave, you have particles or molecules that vibrate about a fixed position and cause the transfer of energy. In electromagnetic waves, you cause a variation in one part of the electric or magnetic field, and that change affects the next point or the next distance through which the medium is transferring the energy or the electromagnetic radiation. Now, for another classification of waves, there is a transverse wave and a longitudinal wave. A transverse wave is a wave where the displacement or the vibration is perpendicular to the wave motion. A longitudinal wave is where the vibration is parallel to the direction of the wave motion or energy transfer. An example for the for the longitudinal wave is the sound waves and the P waves of earthquakes or seismic waves. Transverse waves, we have water waves and all the electromagnetic waves in the electromagnetic spectrum, and we have the S waves in the seismic or earthquake waves. As for describing waves, you have two graphs, one called displacement distance graph and one called the displacement time graph. From a displacement distance graph, you can get the amplitude. It is from the central point or the central position to the top, which is called the crest, or from the central part to the bottom, which is called a trough. And you can get the amplitude. The amplitude is the distance between two corresponding points or two similar points. So this point is similar to this point. So the distance between them is called one wavelength, and the symbol for the wavelength is lambda. From the displacement time graph, you can also get the amplitude, but you can get the periodic time, which is the time for one complete oscillation. If you want to define the amplitude, you say that it is the maximum displacement from the rest position or the undisturbed position. If you want to define the wavelength, it is the distance traveled by the energy or by one crest during one complete oscillation. If you want to define the periodic time, it is the time of one complete oscillation. Now there is another quantity called frequency, which is the number of waves or the number of oscillations per unit time, and you calculate it by dividing the number of waves over time. So if you have 20 waves that pass in 5 seconds, you calculate 20 divided by 5, you get 4 in hertz. The unit is hertz, and we write it as capital H, small z. And frequency is related to periodic time with the equation that the frequency is equal to 1 over the periodic time, but the time must be in seconds. Now there is something called the wave speed. Waves in general move with constant speed through the same medium. So if you have a sound wave that travels through the air, its speed will remain constant. Even if it loses energy in the form of amplitude, not in the form of speed. So we calculate speed by dividing distance over time for constant speed. If the distance is equal to the wavelength, the time will be equal to the periodic time. So we can calculate the speed as wavelength over periodic time. But 1 over periodic time is equal to the frequency. So we can remove 1 over time and replace it with frequency. So speed is equal to wavelength multiplied by frequency. But if the speed is in meters per second, the wavelength must be in meters. If the speed is in centimeters per second, then the wavelength must be in centimeters. Now, if you represent a wave using a diagram, you can draw it from the top view. In this case, you will see straight lines that connect the crests of the waves. This is called a wave front, and the wave front are generally perpendicular to the direction of the wave direction or the energy transfer. So this is 90 degrees, and since each wave front represents crests of a wave, the distance between the wave front is equal to the wavelength. So the wavelength does not change if the speed does not change. So these lines are all equally spaced lines and perpendicular to the direction of the travel of the wave. Now, if you have straight lines as wave fronts, this is called a plane wave or plane wave fronts. And if you have a central object that is very small in size that causes the ripples or causes the wave fronts, then the wave will spread in all directions around that point or the center point of the wave. So the waves will appear to be circular, which is circular curves are perpendicular to all directions from a central point. The curve of a circle is always perpendicular to the radius of the circle. Now you can see the wave fronts by using a ripple tank, which is transparent, and use a light source above the tank and an oscillator or a vibrating object that produces the wave fronts. Now, since water is transparent, you cannot see the wave fronts on the surface of the water, but the light source causes the light to form shadows below the tank, and you observe the shadows using either a stroboscope or a flashing light that has the same frequency as the waves. This causes the appearance of the wavefronts to be stationary even though they are moving. You will see them as stationary if you have a light source that has the same frequency of flashing as the vibrations of the source of the waves. Now we go to the phenomena that happens to the waves. We have reflection, refraction, and diffraction. First, the reflection is the rebounding of waves off a reflecting surface that is made of a different medium. So if you have a water wave that hits a brick wall or rocks, since rocks have different materials than water, the wave will be reflected. And the rule of reflection is that the angle of incidence is equal to the angle of reflection. But the angles are measured from a line called normal to the surface. So you draw a normal line, 90 degrees, to the reflecting surface, and the angle of incidence is between the direction of the incident wave and the normal, and the angle of reflection is the angle between the reflection direction and the normal. And these angles are equal in magnitude. The angle of incidence is equal to the angle of reflection. Now for reflection, you are rebounding in the same medium, so you do not change speed, and the frequency of the waves hitting the surface is the same as the frequency of the waves that are reflected from the surface. So wavelength does not change since speed does not change and the frequency does not change. Well, the only thing that changes in reflection is the direction of the wave travel. Now, to draw the reflection of a wave, you need to measure the angles of the wave fronts. So first, you have a direction that is perpendicular to the wave fronts, and this direction hits the reflecting surface at a certain point. And from that point, you should draw the reflected direction with the same angle. So you have the same angle here as here, angle of incidence and angle of reflection. But the wave fronts themselves are perpendicular to the direction of the reflected wave. So from this point, the reflection would be like this. And in this case, this angle will be equal to that angle. So you draw the reflection of the wave. If you have another wavefront that hits the surface, the reflection would be like this, perpendicular to the direction of the reflected wave. If you have another one, the reflected wavefront will be like this. So this is how you draw the reflection. You use a protractor to actually measure the angles. The angles between the wavefronts and the surface are the same before and after, but in the opposite direction. Now, if you have a circular wavefront, you need to draw the reflection from a central point that is behind the reflecting surface. So if this is the reflecting surface, you must be given the center of the incident waves, and you draw a perpendicular line from that center toward the reflecting surface and extend it beyond. So this is 90 degrees, and you measure this distance and you measure an equal distance behind the surface to get the new center of the waves. And then you use this center with a compass to draw the new reflected waves from the points that hit the surface. So you have an incomplete wavefront here. It hit at this point. Use the compass to draw a wavefront that is in the same space as the incident waves. So the reflections do not appear behind the reflecting surface, they appear in front of the reflecting surface. So the incident waves and the reflected waves are all on the same side. The next phenomenon is diffraction of waves. It is the spreading of waves through gaps or around corners. Now, if the gap is smaller or approximately equal to the wavelength, you get a large diffraction, large spreading, and it appears as if it's a Wi-Fi signal. But the wavelength does not change, so you need to measure the distance between the wavefronts before the barrier or before the hole in the medium, and make sure that the distance is the same all the way through. And then you use a compass from the center of the gap to draw the curves of the diffracted wave. And you make the spreading large if the gap is small. If the gap is wider, you make the spreading less. And if it is too wide, you draw straight lines that are equal to the gap, and then you add bendings at the end of each straight line. So if the gap is very wide, the wave actually passes through as straight wavefronts or plane wavefronts with bendings at the edges. If the gap is narrow, you use a compass to draw curves. But always make sure that the wavelength did not change before or after the gap. The last type of phenomenon is the refraction of waves. The refraction is the change of speed of a wave when it passes from a medium to medium. This can cause bending of waves if the wave is not incident at 90 degrees to the boundary between two media. If the wave is incident at 90 degrees, it will not bend, but the speed will still change, and we call that refraction. Now, when drawing refraction of waves, you make sure that if you are slowing down, you are bending towards the normal, and if you are speeding up, you are bending away from the normal. If you are slowing down, the wavelength decreases, and if you are speeding up, the wavelength increases. Now, if you are incident perpendicular on the surface, there is no bending. You do not bend towards or away from a normal. You are already on the normal, but the wavelength still changes. If you're speeding up, the wavelength increases. If you are slowing down, the wavelength decreases. Now we're going to talk about sound waves. In sound waves, you need to define the sound wave as the compressions and rarefactions of particles. A compression is a region where particles are very close to each other and have high pressure. A rarefaction is a region where the particles are far apart from each other and have low pressure. If you are required to represent a sound wave, you draw layers of waves or particles that are first near to each other, then far apart, then near to each other again. And to label the compressions and rarefactions, you have the rarefaction is the center of the wide spaced area, and the compression is the center of the narrow area. And if you are required to label the wavelength, it is from a compression to a compression, or from a rarefaction to a rarefaction. That is one wavelength. Now, sound is produced by vibrating objects, so any vibrating object emits compressions and rarefactions in the surrounding area. So sound waves are released. And you can say that a sound wave can be represented as a pressure wave. So if you draw a pressure graph, you will have a high pressure at a compression, low pressure at a rarefaction, and the central line would be the atmospheric pressure in the room or the area. Now, sound has several properties. First, it is one of the only types of longitudinal waves we have in the syllabus. The other one is the S waves. or the P waves in the seismic waves or the earthquake waves. Now we have the idea that sound needs particles to compress and move apart to create rarefaction. So if there is no particle in the region or no particles in the medium, then it cannot travel. So sound cannot travel through vacuum because it has no particles or no molecules. And sound actually travels faster in solids than in liquids, and it can travel faster in liquids than in gases. So going from gas to solid, the speed of sound increases. Now, if you have an echo, this is defined as the reflection of a sound waves. So, of a sound wave, sorry. So you have sound bouncing off a reflecting surface and coming back. You hear two sounds. One that is actually emitted from you, then the reflected sound from a reflecting surface far away. You need to be at least 14 meters away or 17 meters away to hear a good echo sound. If you want to display that sound, you need a microphone that is connected to something called a cathode ray oscilloscope that can draw the shape of the sound waves. It transfers the signal received by the microphone. The microphone changes the sound wave into electrical wave, and the CRO draws it on a screen using light. Now, to measure the speed of sound, there are several methods. The simplest method is to have two people a long distance apart, one with a source of light and sound, for example, a flash gun or something that emits light and sound at the same time, and an observer a long distance away that sees the flash of light. So, for example, a puff of smoke, the light will reach the observer much faster than the sound. The sound takes a longer time, much longer time, because the speed of light is much higher than the speed of sound, about 1,000,000 times higher. So the observer measures the time between seeing the light and hearing the sound, and the distance between the observer and the source of sound is measured using a measuring tape. And the experiment should be repeated to account for the reaction time in starting and stopping the timer. And then you have to use a very long distance just to make sure that you can have enough time between starting and stopping the stopwatch. So the precautions are: you use a very long distance, you repeat and take an average for the time measurement. If you are required to say one assumption you made about the experiment, you assume that the time for the light to reach the observer is actually 0, but it is not 0. It is a very small time, but it is not 0. So the assumption is that light did not take any time to reach the observer. The next method is the same idea, using speed equal distance over time, but using an echo instead of two people in front of each other. So the sound travels in a direction, it reflects off a surface and comes back. So it actually travels twice the distance. So for an echo, you use speed is equal to twice the distance over the time, not the distance over the time. And the distance is measured from the source to the reflecting surface. Another method, you can use electronics. For example, you can use two microphones and measure the distance between the microphones and the sound source that will reach the microphone first. The first microphone emits a signal that starts a timer, and when the sound reaches the second microphone, it releases a signal that stops the timer automatically. So you can measure the distance using an accurate ruler or a vernier caliper, and you can use the automatic timer to measure the time, so you do not have a human reaction error in this method. Now you are required to memorize some speeds of sound. In air, it is approximately 340 meters per second, or any number between 300 and 360. In water, it is approximately 1,500. In concrete and steel, it is approximately 5,000 meters per second. You are required to memorize these numbers, so you are able to pick the closest number or the same exact number if it is given to you in a question. Now, for other characteristics of sound, we have something called loudness and pitch. So for a loud sound, you need to have a large amplitude. So if you increase the amplitude, you increase the loudness of the sound, so you have a louder sound. If you decrease the amplitude, you have a fainter sound, or the loudness decreases if amplitude decreases. And the pitch represents the sharpness of the sound. So a very sharp sound or a high pitched sound has a high frequency. A low pitched sound will have low frequency. So amplitude increases, loudness increases, frequency increases, pitch increases, and vice versa. Now, sound is divided into three categories. There is the human hearing range. The human hearing range is between 20 hertz and 20 kilohertz, or 20,000 hertz. Anything under the frequency of 20, it is called infrasound. Anything above 20 kilohertz, it is called ultrasound. The humans can hear between 20 and 20 kilo. Anything below that is called infra. Anything above that is called ultra. Now, ultrasound has many uses. They mostly use echo of ultrasound. We use ultrasound in imaging the internal organs, or imaging babies inside the womb. It uses the reflection of sound from the surfaces. The sound is reflected from each boundary and gives information about the type of tissue inside the body. And the time gives information about the depth. So the longer time it takes for the sound to reflect, this means that the sound wave traveled longer distance. And the detector in turn draws a diagram about the intensity and the depth of the tissue to form a two-dimensional image on a screen. You can also use ultrasound to detect bubbles in metal. So, for example, if this is a metal and this is a bubble, sound can be emitted at the surface of the metal. When it goes through and hits the bubble, some of it is reflected and the rest is transmitted through the bubble. And when it hits the second surface of the bubble, it is reflected back. So you can measure the depth of the bubble and the distance to the bubble. So you can measure the size and the placement of the bubble inside the metal. You can also use echolocation with ultrasound to determine the depth of seawater or the distance of the seabed from the surface. You can also use the equation speed equal twice the distance over time. If you already know the speed of sound in water and you measure the time of the reflection, you can calculate the depth of the sea at this region. This chapter talks about the properties of electromagnetic waves and light. First, we say that we have 7 types of electromagnetic waves, which are in turn radio waves, microwaves, infrared radiation, visible light, ultraviolet rays, X-rays, and gamma rays, which you are required to memorize in order. And the visible light has 7 colors: red, orange, yellow, green, blue, indigo, and violet. We are also required to know the uses of each type of radiation. For example, for radio waves, we have TV and radio stations, and we also use radio waves in Bluetooth connecting devices like Bluetooth headphones or Bluetooth data connection between 2 cell phones. And we also use it in VHF or UHF channels on the local television or satellite televisions. We can use radio waves also in RFID cards, which stands for radio frequency identification cards, which are like the credit cards or debit cards, and the cards we use in hostels or anything like that to identify that you are a member and you can come inside the building. And we use it for wireless internet over short distances. This is because radio waves have low frequency and low energy. They cannot penetrate through walls and they cannot travel long distances. So they are used for local data transmission. If you want the data to travel much longer distance, you need higher frequency, which is present in the microwaves. So we use microwaves in satellite communications and cell phone communications. We also use microwaves in microwave ovens, in which they are directed towards the food, and the water and fat molecules in the food vibrate faster or resonate with the wave, and start gaining kinetic energy, so the temperature of the food increases inside the oven. As for infrared radiation, it is mainly used for heating purposes or for infrared transmission inside optic fibers. We use visible light or infrared in optic fibers to transmit information or digital data in internet cables. We can also use infrared radiation in remote control signals, since infrared has a wide range of frequencies, so we can make each remote controller have its own frequency. As for visible light, we use it mainly for seeing or recording what we see in photography or filmography. We can also use light in optic fibers to transmit internet data, and we can use it to heat objects. Next is the ultraviolet radiation. It is produced by sparks and stars or arcs or flames. We use it on Earth to detect fluorescent chemicals absorbed by the materials when skin is in contact with it. So you can detect with it any fingerprints or footprints, or we can use invisible markers to mark anything we need to mark for security, and then use a UV lamp over the material to detect the light emitted from the substance or from the ink we use in the on the material. Another use, it's not very important, but we use it to tan our skin. Tanning is the change of color and the reflectiveness of the skin color. Because ultraviolet rays are harmful, they have very high frequency. They actually can cause skin cancer if you are overexposed to ultraviolet rays. So the UV lamps used for tanning, they are actually harmful, but you can also use ultraviolet to kill the cancer cells or the mutated cells on the skin. As for X-rays, we use X-rays in security machines to detect objects inside a suitcase or a bag. We can use them also to detect or image bones inside the body. So the idea is that X-rays can penetrate low density. So if you have a low density material, X-rays can go through it. If you have high density material, X-rays are absorbed and blocked and they cannot reach the other side. If you have a film or a fluorescent film, the film will get burned on this part, but it will stay bright on the part that represents the bone, which has high density. That is the idea of the X-ray machine. And for gamma radiation, it is emitted from the unstable nuclei. We use gamma radiation in the uses we mentioned before in the previous chapters about atomic physics and radioactivity. Now, all electromagnetic waves have common properties. They are all transverse wave. They are all electromagnetic. They represent variation in electric and magnetic fields, and they do not need a medium to travel. They can travel through vacuum, but they also travel through other media. And they all have the same speed in vacuum or in air, which is 3 × 10⁸ meters per second. And they are all reflected, refracted, and diffracted. Unless the wavelength is very short, which is in the case from visible light to gamma radiation, they need very small gaps or very narrow gaps to diffract through. So diffraction does not appear very often in light and ultraviolet, X-rays, and gamma rays. They can be emitted or absorbed by surfaces or materials. As for light, to see an object, you need light to be emitted from the object. For example, light to be emitted from a lamp or a screen towards the eye. So light reaches the eye and it stimulates a signal inside the brain that tells you that you are seeing something. Or if you are talking about an opaque object that does not emit its own light, there must be light that was incident on it, then it was reflected, then entered the eye. So the eye is convinced that the light is coming from the object, not from the light source. So light must enter your eye to see anything. Now there are three types of waves: parallel beam or parallel rays. There are diverging rays which are spread out or spreading out. There are converging beams or converging rays that are concentrated at one point. They may continue and diverge after that, but they meet at one point. This is called a converging beam of light. As for the colors of light, we have different colors representing different frequencies or different wavelength of color. If you have a full spectrum of color, you create white light, so from red to violet. If you have all colors coming together on the same line, you will receive white light, or you will receive a partial spectrum. You will see a specific color or a range of colors. And if you have one color, then we call that monochromatic light. But if you are required to define monochromatic light, you say that the monochromatic light is light of a single frequency or a single wavelength. Now, light follows the same rules of reflection. So when reflecting light, there is an angle of incidence between the incident ray and the normal, and the angle of reflection between the reflected ray and the normal, and the angle of incidence is equal to the angle of reflection, as always in waves. For reflection in a plane wave, in a plane mirror, you have an image that you see in the mirror, or an image that you receive in the retina of your eye. The images are two types. There is a real image that can be formed on a screen, and there is a virtual image that can be seen but cannot be formed on a screen. A real image is formed when real rays of light actually intersect, and the position of the image is the position of the intersection of rays. A virtual image occurs when the rays actually are diverging, and you need to extend the rays backwards to find the intersection. If the image is formed by the intersection of extensions of rays, it is called a virtual image. If the rays themselves intersect, then it forms a real image. As for the reflection in a mirror, there are two types of mirrors. There is a curved mirror and there is a plane mirror. For a plane mirror, if you place an object in front of a plane mirror and you look at the mirror to see the image appears behind the mirror and it appears upright, and it is virtual since the rays actually diverge. If you have two rays coming from one point of the object, the reflections diverge and they appear to meet behind the image. But if you place a screen behind the image, behind the mirror, you will not receive any light behind the mirror. So it is called a virtual image. And the distance between the object and the mirror is equal to the distance between the mirror and the image. And the image is the same size as the object. So it is virtual, upright, beyond the mirror or behind the mirror. Same distance between the image and the object is the same as between the image, the object and the mirror. Or the distance between the object and the mirror is the same as the distance between the mirror and the image. And the image is laterally inverted. This means that anything on the left will appear to be on the right. Anything inwards towards the mirror will appear to be outwards, coming out of the mirror. This is called lateral inversion. If you are required to label the arms of a clock on the wall that is appearing on a mirror, or this is the image of the clock inside the mirror, you just count the numbers on the clock, but not clockwise. You count them anti-clockwise. So this is 12, 1, 2, 3. Instead going this way, you go the other way. Now we can use plane mirrors in a device called a periscope. A periscope, you have a pipe and a mirror that is angled at 45 degrees to the edges of the pipe, and another mirror that is parallel to the original mirror. So when light is incident on one mirror, it has an angle of incidence 45, so the angle of refraction is also 45. So it bends with 90 degrees. Then it does the same exact thing. It bends with 90 degrees total, 45 incident and 45 reflection, until it reaches the other end of the periscope. And you can use that periscope to look over a wall, or it is also used in submarines to see above the sea level or the sea surface while the submarine is below the surface. Now, when you are asked to construct an image or use rays to find the position of an image, you are given the position of an object. You draw two incident rays that are random towards the mirror, and you use the ruler and the protractor to measure 90 degrees on the mirror surface to draw a perpendicular line that extends beyond the mirror from the object. Now you measure this distance equal to the distance behind the mirror, and you label the point of the image or the position of the image. The reflection from these points on the surface of the mirror should have an extension that goes to the image. So you just draw straight lines that go from the image towards the intersection point and extend outwards. The same with the second ray, and you go outwards, and you draw normal lines using the protractor perpendicular to the mirror, and you will find that these angles are equal and these angles are equal without actually using a protractor to measure the angle of incidence and angle of reflection. So each ray was reflected, and the extensions going backwards behind the mirror, you find the intersection of the image. If you are given a curved mirror, you must be given the center of the curvature. And if you have an object at this position, you also draw two random rays towards the mirror. And this case, you don't know where the image will be, so you need normals and you need to actually measure angles. But the normal on a curved surface comes from the center of the curve. So you connect the center of the curve with the intersection of the ray, and you measure the angle of incidence, and you measure an equal angle of reflection. So you draw the reflected ray as long as possible. And you do the same thing with the second ray. So this was the first ray, the second ray met the mirror at this point, so you draw a normal from the center towards this point, and you also measure the angle of incidence and measure an equal angle of reflection, and you draw the reflected ray. The position of the intersection is the position of the image. Now we talk about refraction of light. Refraction is a change in speed of wave. In this case, it is a change of speed of light, of a light ray, when it moves from a medium to a medium. It is usually a transparent medium if we're talking about light, like water, glass, plastic, diamonds, or anything that is transparent. Now, why does images appear to be at a different position from the object when you look at them from the surface of water? Because as light exits the water, it bends a little as it changes speed. Going from a denser medium to a less dense medium, the speed increases. So light has higher speed in less dense media, but sound has higher speed in more dense media. So as the light bends towards your eye, it appears that the light is coming from another point than the original position of the object. Now, to calculate the angles, we have different types of calculations. We have something called the refractive index. The refractive index depends on the medium or the density of the medium. If the density of the medium is high, the refractive index is high. If the density is low, the refractive index is low. The definition of refractive index depends on what type of refractive index is it. Is it a refractive index of a medium, refractive index of glass, refractive index of water, or something like that? Or is it a refractive index of light? If you have refractive index of a medium, or it says that oil has a refractive index of 1.4, for example, the refractive index is calculated as sine the angle in air divided by sine the angle in the medium, or the speed of light in air divided by the speed of light in the medium. If you have a refractive index of light, regardless of the type of medium, you calculate sine the angle of incidence divided by sine the angle of refraction. So if the light is moving from air to water, the incident is in air and the refracted angle is in water. So you divide sine the angle of incidence in air over the sine of the angle of refraction in water. If you're moving from water to air, it will be reversed. But refractive index of a medium, it is never reversed. Air is always on the top and the medium on the bottom. For refractive index of light, you place the incidence at the top and the refraction at the bottom. Now, the bending happens just like for waves. If you're speeding up, you bend away from the media, from the normal. If you are slowing down, you bend towards the normal. And refraction is always accompanied by some reflection in light. So always part of the wave refracted and part of the wave reflected. The angle of incidence and reflection are always equal, but in the less dense medium, the angle is greater than the more dense medium. So the angle in air would be greater than the angle in glass or water, because water is more dense than the air. If you are incident at 90 degrees to the surface of the boundary between two media, then it is said that the angle of incidence is zero, or you are on the normal of the surface, so there will be no bending because the angle of incidence will be zero, so the angle of refraction will also be zero. So if you're incident perpendicular to the surface, you will not bend, but you will still have a change in speed. Now, if you have a parallel sided block, like a rectangular block, the angle of incidence outside the block decreases to an angle of refraction which is less inside the block, because the block has higher density than air. So the light bends towards the normal, and moving outside of the block, it bends away again from the normal. But the incident ray is parallel to the emerging ray. It's always parallel to the emerging ray. The only ray that is in a different direction is the ray inside the block. If you have another ray that is parallel to the original one, it will bend with the same angle and then go parallel to the original direction again. For a rectangular prism, the sides of the entrance and exit of the ray are not parallel, so the incident ray and the emerging ray are not parallel to each other. There is a deviation in the direction of light. So as you go into the prism, you bend towards the normal, you go closer to the normal, and as you exit the prism, you go away from the normal because you are speeding up. In this case, if you have a monochromatic light, you will have a single ray going into the block, bending, then going out of the block, bending further. But if you have white light, you will experience dispersion of light, which is the spreading of light or the division of light into a spectrum of colors due to the change in speed, because different colors move with different speeds in different media. But in air, they all travel with the same speed. So outside the prism, they all have the speed 3 times 10 to the power of 8. But inside the prism, they have different speeds, and different speeds cause different bending angles. So red is always bent the least amount, and violet bends the most amount. So you will always have red closer to the original direction and violet very far from the original direction. Always red bends more than violet. So going with the colors rouge biv, red, orange, yellow, green, blue, indigo, violet. Going towards violet, the bending gets larger. Going towards red, the bending gets smaller. If you use two identical prisms, you can recollect the white light. After dispersion, you can recollect it to white light again, because you have parallel sided exit and entrance. So the light will go in the same original direction. So the light rays are refracted towards each other or bend towards each other, and they are recollected to form the new white light ray after dispersing. Now, if you have white light that has infrared and ultraviolet with it, you will find that the infrared part will be just next to the red and the ultraviolet just next to the violet. Infrared means frequency that is less than the frequency of red. Ultraviolet means that it has a frequency that is higher than violet. So they are compared to the colors in the visible spectrum, so they will be right next to their names in the visible spectrum. Now we talk about semicircular blocks. If you have a ray of light that is directed towards the center of the curvature of the block, the ray of light will have an angle of 90 degrees with the surface as it enters the block. Or if you have a ray of light that is coming from the center and going out of the block, it will also be incident at 90 degrees with the surface, or incident normal to the block. So the angle of incidence is actually 0. So there will be no bending at these points. but still you will have a refraction, which is a change in speed. So when you enter perpendicular to the surface, you do not change in direction, and that happens in the curvature of a semicircular block if you are directing it towards the center of the curvature of the block. Now at the flat side, you will always find bending will occur. If you are going from outside the block to inside the block, the ray bends towards the normal as it slows down. If you are going from inside the block to outside the block, the ray bends away from the normal since you are speeding up. In the case of going from a less dense medium to a more dense medium, you will always bend towards the normal. The speed decreases, so you bend towards the normal. But if you go from a more dense medium to a less dense medium, the speed increases and you bend away from the normal, which means eventually you will reach the surface of the boundary between two media. If the angle of incidence does not cause you to go on the surface, it causes you to refract normally, we call that this angle is less than the critical angle. If the angle of incidence is that gives an angle of refraction 90 degrees, which means that the ray goes on the surface, we call the angle inside the medium or the denser medium the critical angle. So if the angle of incidence is equal to the critical angle, the refracted ray will be on the surface of the boundary between two media, or it will have an angle of refraction 90 degrees. So the definition of critical angle, it is an angle of incidence that gives an angle of refraction of 90 degrees. If the angle of incidence is less than the critical, you have a refraction that is away from the normal. If the angle of incidence is greater than the critical, you have no refraction and all of the light is reflected. In the previous examples, we have some reflection here, we have some reflection here, but here all the wave or all the light is reflected. This is called total internal reflection. So total internal reflection occurs when the angle of incidence from a denser medium to a less dense medium is greater than the critical angle. All of the light is reflected back inside the medium. And we can use the equation for refractive index of a medium to calculate the critical angle. Since the angle of incidence is the critical angle and the angle of refraction is 90 degrees, sine 90 is actually 1. So the refractive index is equal to sine 90, which is 1 over sine the critical angle, which gave the angle of refraction 90 degrees. So this is the equation that relates refractive index and critical angle. We can also say that the critical angle, sine the critical angle is 1 over the refractive index, and then we use inverse sine. So the critical angle is inverse sine of 1 over the refractive index of a medium. We use total internal reflection in reflecting prisms, where the prism is 45 and 45 degrees from two sides and 90 degrees from one side or one edge, where light enters at an angle of 90 degrees and goes through the prism. And when it hits the inclined plane with two 45 degrees angles, it is totally internally reflected because the angle of incidence is greater than the critical angle. Now we can use the prism with different orientations and they all include total internal reflection. You just have to follow the ray, and from the inclined surface you have the reflection of 90 degrees total, 45 incidence and 45 reflection. And we use these prisms also in periscopes, just like the mirrors. The angle is 45 and the reflecting surfaces are parallel to each other, but the light has to enter inside the prism to be totally internally reflected. Another device that uses total internal reflection is the optic fibers. The optic fibers are very thin glass fibers where the light enters from one side and it keeps experiencing total internal reflection until it exits from the other side. When drawing the normals at the edges of the fiber, you must make sure that the angle of the normal is 90 degrees to the curvature, so the curvature here is inclined, so the normal will be also inclined. Then by best judgment, using your eye, not a protractor, you measure an angle which is equal not using a protractor again, to measure an approximate reflection for the ray of light, and the angle of incidence is always equal to the angle of reflection. Now, two devices that use optic fibers are internet cables, which send signals of digital data as flashes of light instead of high voltage and low voltage, so high intensity of light and low intensity of light, or high intensity of infrared and low intensity of infrared, to send digital data across a cable, an optic fiber cable. Or we can use an endoscope, which uses two fibers inside its structure. One fiber to get light to enter the body, since the body is not illuminated inside. Then the light reflects from the surface of an organ and enters another fiber and goes back to the doctor or the investigator, which images the internal organs of the body. And the light is traveling by total internal reflection inside the optic fibers. Now we go to lenses. We have two types of lenses, a biconvex lens and a biconcave lens, and we have to memorize three types of rays for the convex lens. If a ray is incident on the optical center of the lens, which is at the center of the lens and on the principal axis of the lens, which is perpendicular to the curvature of the lens from both sides, this ray does not bend at all. It goes straight through the optical center and in the same direction through the other side. If you have a ray of light that is parallel to the principal axis, it goes to the central line of the lens and then bends towards a point called the focus point, which is a distance from the center of the lens called the focal length. So the focal length is the distance between the optical center and the focal point on the principal axis. And if you have a ray that passes through the focal point before the lens, when it reaches the central line of the lens, it bends and goes parallel to the principal axis. So these rays are reversed actually. As for this ray in a concave lens, it does not go towards the focal point on the other side of the lens. It appears to come from the focal point on the same side of the source of light. So if you have a ray that is parallel to the principal axis in a concave lens, it does not bend towards the principal axis. It bends away from the principal axis, and it does not go to the focal point on the other side. It appears to come from the focal point on the same side as the light. Now for drawing the images of the objects in a convex lens, if you have an object which is like this, represented by an arrow, if the tail of the arrow is on the principal axis, the tail of the image will be also on the principal axis. You draw two rays. You need only two rays to find the image, one that is parallel to the principal axis and then goes toward the focal point. So you bend this light towards the focal point, which should be given in the question, and you extend that line as far as possible. And the other ray, which passes through the optical center and passes straight through, it does not bend, and you keep extended these rays until you reach the intersection point of the rays. You draw an arrow before the lens and an arrow after the lens or beyond the lens, and the intersection point represents the head of the image, and the tail of the image is actually on the principal axis. Now this type of image is inverted, magnified, and is a real image since the rays themselves intersected. So you have a real image whenever the rays intersect by themselves without having to extend the rays beyond the lens. Another case is that you have the object between the focal point and the center of the lens. So if the object is at this position, you draw the same two rays. The ray first at you draw a parallel beam of light or ray of light to the principal axis. Then this ray of light goes to the focal point. But in this case, you will find that the other ray will not intersect with it. So you have to extend this ray backwards. And the other ray is going through the optical center from the top of the arrow, and it goes straight through, but still you have no intersection, so you have to extend it backwards. And you draw the extensions as dashed lines, not as solid lines, to represent that this is not the real ray of light. You draw arrows before and after the lens, before and after the lens. and the intersection point is the position of the image. And since the tail is on the axis, the tail of the image will be on the axis. Now this type of image is magnified or enlarged and upright, and it is virtual because it is made of extensions of rays. So whenever you place an object beyond the focal point, you will get a real image that is inverted. It could be larger if it is between twice the focal length and the focus. If it is beyond twice the focal length, it will be smaller, but it will be real and inverted. And if you have an object that is between the focal point and the lens, it will always be magnified, upright, and virtual. As for the concave lens, if you have an object that, for example, is pointed here, you draw two rays, one that is going through the optical center. This ray goes straight through the optical center with no bending, and the other ray is parallel to the principal axis. You draw it until you reach the central point or the central line of the lens, and you draw the ray extended from the focus that is on the same side of the object and goes towards the intersection point here and goes upwards. But this part behind the lens or on the same side as the object, this is actually an extension of the ray. So this is the ray behind the lens, this is the ray before the lens, this is before and this is after the lens. And the intersection now is between a real ray and an extension of a ray. And this is from the top of the arrow, so this is the top of the arrow, and the tail is on the principal axis for both the image and the object. Any intersection with an extension, even if you have another ray that is real, it is considered a virtual image. So this image is smaller than the object or diminished. It is upright and virtual. Next, we talk about sight correction. If you have a short-sighted person, this means that the ray intersects before the retina. You need a concave lens to correct that. It makes the rays diverge and then converge at the right position at the retina. If you have a long-sighted person, that means that the intersection of the rays without a lens, they meet behind the retina or beyond the retina. You need a convex lens to make the rays converge more to meet at the correct position of the retina. Now the last chapter in the syllabus is about astrophysics and space. The first section is about the solar system and the information about the solar system. So we need to know that our solar system consists of one star called the Sun and 9 planets or 8 planets and 1 dwarf planet. The first 4 planets are called the inner planets, which are in sequence Mercury, Venus, Earth, Mars, moving away from the Sun. So the closest planet is Mercury. After Mars, there is an asteroid belt around the Sun, and then there is the orbit of Jupiter, then Saturn, then Uranus, then Neptune, and Pluto is actually considered now a dwarf planet. So the 4 planets after the asteroid belt are called the outer planet, and before the asteroid belt are called the inner planets. And we should know that all the planets are rotating or orbiting around the Sun in one disk, in one direction. They are all orbiting in one direction. This disk is called an accretion disk. We should know that the Sun consists of most of the mass of the solar system. It has about 99.9% of the solar system, and the heaviest planets are Jupiter and Saturn in our solar system. We should know that the orbits, as they go away from the Sun, the radius keeps increasing in size. Actually, it could be double the size or more than double the size. Starting from Jupiter, the radius gets much larger than before Jupiter. Mars and Earth and Venus are considered very close to the Sun or the center of the solar system. Now, the components of the solar system are the star, which is mainly made of hydrogen and helium gas. This is the fuel of the star in this stage of its life. So the fuel of our Sun is the helium gas that changes into hydrogen by fusion reaction. and the energy released from the reaction or the fusion reactions that happen in the core of the star is released from the surface as electromagnetic radiation. But the three most emitted radiations are infrared, which is heat, visible light, which reaches us as white light, and ultraviolet radiation. Other ranges of the electromagnetic spectrum, magnetic spectrum are emitted, but these three are emitted with maximum intensity. As for the inner planet, we call these planets rocky planets. They have high density. Mercury is the smallest planet and the closest planet to the surface of the sun. Venus is next, and Earth is next. This is the third planet. Mars is the fourth planet, and it has a mass much less than the Earth. Mercury is actually the one with the smallest mass and the one with the smallest gravity. You should know that Venus and Earth have approximately equal diameters and approximately equal masses. They even have approximately equal gravity field strength on their surfaces. But the Earth is at a suitable distance from the Sun to have solid, liquid, and gas water on its surface, which supports life. So if you're asked why is Earth the only planet with life, it contains liquid water. It is the only planet with liquid water in it. Before the Earth, nearer to the Sun, you cannot have liquid water. You only have vapor water or gas water. Beyond the Earth, the water changes into ice, or it is in the solid state, so you do not have liquid water on Mars. There could have been liquid water before, but now there is no water on the surface of Mars. There are ice caps on Mars though. Mercury has no atmosphere and is full of craters. Venus, Earth, and Mars all have atmospheres, but Venus has sulfuric acid and carbon dioxide, which causes large amount of heat building up due to global warming. So even though it is not the closest planet to the surface of the sun, but due to global warming, it has the highest temperature in daytime due to global warming and the trapping of heat inside the atmosphere of the planet. Earth has air as atmosphere. Carbon dioxide is the most component in the atmosphere of Mars. As for the outer planet, Jupiter and Saturn are considered gas giants since they are mainly consisting of gases, and there is no solid surface on Jupiter or Saturn. Uranus and Neptune are called ice giants because they have solid surfaces that are made of ice. Ice in space does not have to be specifically made of water. It could be solid carbon dioxide or any solid gas that is in our room temperature in the gaseous state, but at a distance far from the sun it would be very cold, so it will turn into the solid state, it will freeze. Now, Saturn and Uranus and Neptune all have ring systems that are made of moonlets, small moons that orbit around the planet in a disk, in a accretion disk. But Uranus has a disk that rotates at 90 degrees to the axis of the accretion disk. Saturn is has an inclined disk. Neptune has an approximately horizontal disk, but they all have disks. But Saturn has the most visible moonlet or moon system around it that creates a visible disk around the planet. Now, comparing the information between the planets as the distance from the sun, which is the radius of the orbit of the planet, and the orbital time, you will find that the further away the planet gets from the center of rotation or from the sun, the smaller the speed of rotation, or the longer the time it takes to complete one cycle around the sun, which is called year. As for the temperature of the surface, you will find the further away you get from the sun, the smaller the temperature of the surface of the planet, except for Venus due to the global warming of its atmosphere. As for the density, we said that the first inner planets are made of rocks, so they have the highest densities. Going away from the sun, you will find the gas and ice giants with a smaller density, much smaller densities than the rocky planets. And for the mass, it affects the gravitational field strength. You will find that the gravity field strength is proportional to the mass of the planet. The heavier the planet, the greater the gravity on the surface of the planet. So this is a comparison. You are not required to memorize these numbers, but you are required to use the numbers given to you to compare the effects on temperature, on the orbital time, and on the gravity field strength. So, mentioning that the gravity field strength depends on mass, it also depends on the distance from the center of the gravity field. So, the center of the gravity field of the solar system is the sun. Moving away from the sun as a distance increases, the gravity of the sun at that distance decreases also. This is what causes the time of the period of orbit to increase. So if you are asked why does it take more time to orbit the sun at a longer distance, or why does Jupiter has a longer time of orbit than Mars? Because it is further away from the sun, so there is weaker gravity at the orbit of Jupiter than at the orbit of Mars. Now, these orbits are not circular, are not perfect circles, they are approximate circles. They are called elliptical orbits. They have two centers, and the sun is at one of the centers of the ellipse. Also, the orbit of a moon around a planet is also elliptical. The center of the planet is at one of the centers of the ellipse, and the moon orbits in an elliptical orbit around the planet. Now we can approximate the shape of the orbit to be circular, but it is not an exact circular orbit. It is an elliptical orbit. As for the dwarf planets, a dwarf planet is mainly a large rock that is large enough to not be an asteroid, but not big enough to be a planet, and it is not perfectly spherical. Some asteroids have a spherical shape. Rocks like asteroids have a range of diameters and range of sizes. They can range from a boulder to a size of 10 kilometers wide or many miles wide in diameter. So the larger ones are called dwarf planets, and they orbit the sun in elliptical orbits as well. Other objects that orbit around the sun are comets. Comets are mainly made of dust and ice, and they have a tail that is always pointing away from the sun, because the sun vaporizes the ice and it creates the tail as a gas trail behind the comet, not in the opposite direction of travel of the comet, but it is always pointing away from the sun as vapor. The orbit of a comet is highly elliptical. It is not an approximate circle. It is highly elliptical. You cannot mistake an orbit of a comet to be circular. Sometimes it goes right away from the sun outside the orbit of Neptune and comes closer to the sun, even closer than Mercury, then moves away again. As it gets closer, the speed of the motion increases, which means that the kinetic energy of the comet increases. As it moves away, the speed of the comet decreases, kinetic energy decreases. This is because as you move away from the center of gravity of the sun, you gain gravitational potential energy, so you must lose kinetic energy. Or you say that the kinetic energy is converted into gravitational potential energy. And as you move closer to the sun, you lose gravitational potential energy. So this gravitational potential energy is converted to kinetic energy. So moving closer, you lose GPE and gain kinetic. Moving away from the sun, you lose kinetic and gain gravitational potential energy. Now we're going to talk about the gravitational fields of planets and stars. The gravity field is a region where a mass experiences a force, and the field strength is the force per unit mass. It is the force on 1 kilogram due to the gravitational force. So the gravitational field strength is larger when the mass of the planet is greater. So the G is proportional to the mass of the planet. And it is also dependent on the distance from the center of mass of the planet. So the further away you get, the weaker the field gets. This is represented by the spacing between the lines. The field lines are closer at the surface and wider apart going away from the surface. This means you have a strong field near the surface or close to the center of the planet, and you have a weaker field away from the surface, or the further away you get, the weaker the gravity gets. Now, this gravitational field causes a gravitational force which is called the weight, and this force is the source of the centripetal acceleration of anything in orbit, in an orbit. So in an orbit, use the gravitational force as a centripetal force, and this keeps the objects rotating or orbiting around each other. So it keeps the planets orbiting the sun, or asteroids or comets orbiting the sun. This is a gravitational force. And the gravitational force also used to keep the moons orbiting around the planets. So for example, you have the moon orbiting around the earth. If this is the direction of the velocity, this is the direction of the gravitational force and the acceleration of the moon. They are always 90 degrees to each other, the speed and the centripetal force towards the center of the planet. Now you can calculate the speed of the orbit by dividing the distance traveled by the time, but if you consider the orbit to be an approximate circle, you will calculate the radius of the orbit, which is the distance from the center of the planet to the center of the orbiting object. This is the radius. And you use the equation for the circumference, since the distance will be the circumference of the circular orbit, or the approximately circular orbit. So you use 2 pi r, which is the equation for the circumference, divided by the periodic time of rotation. So if you have the radius of the orbit of a planet, you multiply it by 2 pi, then you divide by the time it completes one cycle around the sun. Or for a moon, you use the time that it completes one cycle around the planet. For example, for the Earth, the time to complete a cycle around the sun is 1 year, which is 365 days. Then you multiply by 24 hours, multiply by 60 minutes, then 60 seconds. Or for a moon, it is for Earth, we have one moon that orbits around the Earth in 1 month, or approximately 28 days. So 28 days multiplied by 24 multiplied by 60 by 60 to convert it into seconds. Now there are many types of orbits. In our syllabus, we have to focus on one particular type of orbit. It is called the geostationary orbit. It is above the equator. It is a distance always above the equator, and it has the same angular velocity or angular speed as the planet. It rotates in the same direction as the planet and with the same angular speed. So it appears to be always above the same point on the planet. This is used in satellite dishes and satellite channels. If you have a satellite dish above your building, you will find that it is always pointing in the same point, because the satellite is always at the fixed position. Even as the Earth rotates, the satellite rotates around the Earth with the same angular speed, so it appears to be above the same point at all times. So the conditions for a geostationary orbit is that the satellite should be above the equator, rotating in the same direction as the rotation of the planet, and with the same angular speed or with the same periodic time as the rotation of the planet about its own axis. Now, what happens if you release a satellite with a velocity that is less than the required? So to orbit in a constant radius circular path, you need to have a specific speed. If the speed decreases, the orbit becomes too low, and eventually the satellite will hit the surface of the Earth again, as if you are throwing a rock vertically upwards, but with a small angled incline parallel to the surface, so it will move in a curve and then go back to the surface of the planet. If the speed is too high, the satellite will spiral outwards and then it will get lost into space. Now we're going to talk about some phenomena on Earth that are experienced due to our position in the solar system and the motion of the planet around the sun. So the first phenomenon is the existence of daytime and nighttime. This is caused when part of the planet is facing towards the sun and the other part is facing away from the sun. So the part facing the sun experiences a daytime and the part facing away from the sun experiences nighttime. So this is caused by the spin of the Earth around its axis. Each part of the planet sometimes is pointing towards the sun and sometimes is pointing away from the sun. But why do different parts of the planet experience longer daytime or shorter daytime? The parts that are pointing toward the sun due to a tilt in the axis of the axis of the Earth is tilted at 23.5 degrees. So the parts that are pointing toward the sun will experience a longer time exposed to sunlight, so a longer daytime, and a shorter nighttime exposed away from the sun or not exposed to the light. And the parts that are pointing away from the sun will experience a short time in sunlight and a longer time away from the sun, so longer night time. So if you're asked why is there a daytime and nighttime, because the Earth spins around its axis and each part of the planet sometimes faces the sun and sometimes faces away from the sun. Why do different parts on the planet experience longer and shorter daytimes? Because of the tilt of the axis of the planet or the spin of the Earth. So some parts spend more time exposed towards the sun and some parts spend less time exposed towards the sun. As for the seasons depend on the amount of exposure to sunlight. So if you are in summer, you are exposed to sunlight for a long time. If you are in winter, you are exposed to sunlight for a shorter time. This also depends on the curvature or your position on the Earth. Since the Earth is tilted or the axis of the Earth is tilted, sometimes one section would be pointing towards the sun and at another time of the year it will be pointing away from the sun. So this is high or long exposure to sunlight. So this is summer, and this is a short exposure to sunlight. So this is winter at that part of the Earth or of the planet. The seasons are reversed on the top and the bottom of the planet. So the upper hemisphere would have summer in this area, and the lower hemisphere would have winter because it's pointing away from the sun. The upper hemisphere would have winter at this time of the year, and the lower part or the lower hemisphere will experience summer because it is pointing towards the sun. So the seasons depend on the time of the orbit of the Earth around the sun, which takes 1 year. The year is 365 days, and on the tilting of the Earth axis. So some parts will experience summer and some parts will experience winter. In the middle between summer and winter, you have equal day time and night time. So they are in the middle. That is the spring and the autumn seasons. Now, the next phenomenon we observe on Earth due to our position is the phases of the moon, or how we see the moon. The phases of the moon are a new moon, a waxing crescent, a first quarter, a waxing gibbous, full moon, waning gibbous, third quarter, and waning crescent, and it repeats from new moon again. Now, a new moon occurs when the moon is in the middle between the sun and the Earth. So we see the dark side of the moon, and the illuminated side of the moon is facing away from the Earth, so we don't see it. That's why we see a dark circle, or we don't see the moon at all. So when the moon moves a little angle away and the light actually can reach the moon and reflect towards the sun, so we see a little bit of the moon side that is illuminated. That is the waxing crescent. So the amount of light increases according to our view on the moon until the angle increases to 90 degrees. That is the first quarter. We see the moon half illuminated. And as the angle increases, we see more of the moon illuminated until the Earth is in between the sun and the moon. We see the moon fully illuminated, and that's a full moon. That's half a month, or approximately 14 days. Then the amount of light decreasing as the angle passes 180 degrees. That's a waning gibbous. And then it's a third quarter. So half the moon is again illuminated, but the other half of the moon. And then it's a waning crescent. And then we go back to a full moon. Now we only see one side of the moon, since the moon spins about its axis at the same rate as it spins around the Earth or orbits around the Earth. So it takes about 28 days to orbit the Earth, and it takes about 28 days also to rotate about its axis. So we only see one side of the moon, and the other side is always hidden, pointing away from the Earth. Another thing we see from Earth is meteors or meteorites. Meteors are interstellar objects that collide with the atmosphere, and due to friction they burn up as they enter the atmosphere and pass through, or we hit the Earth hits the path of their motion or their orbits, or our orbit intersects with the orbits of these asteroids or small rocks in space, or interstellar dust in space. If the meteorite or the meteor is large enough that it does not burn up during entering the atmosphere, and its trajectory is pointing towards the surface of the Earth, it actually hits and leaves behind a solid lump we call a meteorite. So a meteor is an interstellar object or stellar object that burns up while moving through the atmosphere due to friction. If it leaves behind a solid object that cools down, the solid object is called a meteorite. Now we go to a piece of information about distances in space. The distances in space are very large or very wide, so we need a larger unit than meter to calculate it. So we need something that is called a light year. A light year is the distance traveled by light during 1 year, and we can calculate that using distance equals speed multiplied by time. So the speed of light is 3 times 10 to the power of 8, and the time of 1 year is 365 days multiplied by 24 hours multiplied by 60, then by 60 minutes and seconds. Then we get a value which is approximately 9.5 times 10 to the power of 15 meters. That's 1 light year, or we can call it 9.5 times 10 to the power of 12 kilometers. So if we need to measure the time traveled by light through a distance or through a certain distance, for example, the distance between the sun and the Earth is 1.5 times 10 to the power of 11 meters, and we know that the speed of light is 3 times 10 to the power of 8 meters per second. So we calculate the time as distance divided by speed, which is equal to 1.5 times 10 to the power of 11 divided by 3 times 10 to the power of 8. That gives a value of 500 seconds. That's approximately 8 minutes. So this is how you calculate the time that light takes, distance over the speed of light, and this is how you calculate the light year, or you are actually required to memorize that it is 9.5 times 10 to the power of 12 kilometers, or 9.5 times 10 to the power of 15 meters. Now going beyond our solar system is part of a large galaxy. Galaxies are clusters of stars that orbit around the central point and are held together by gravity, by the attraction force of gravity between the stars and all the objects and the dust in the galaxy. A galaxy can contain up to hundreds of billions of stars, and our star is just one of these hundreds of billions of stars in our own galaxy, which is called the Milky Way, and our position in the galaxy is approximately midway between the center of the galaxy and the edge of the galaxy. Now we go to something called the life cycle of stars, how stars are formed and how they die, and what happens when they finish the fuel that gives them their energy. So at the start, the star is not actually a lump of mass or a spherical object. It is a cloud made of hydrogen gas called nebula, and this nebula contains many particles, millions and billions of particles that are attracted over long periods of time by gravity. They are attracted to each other, and the nebula keeps collapsing and compressing, and its size keeps decreasing. Eventually, the decreasing potential energy between molecules causes the kinetic energy of the molecules to increase. And as the kinetic energy of the molecules increases, the temperature of the cloud keeps increasing, and the speed of the particles as they move towards each other increases, which eventually causes the start of fusion reaction. And we call a nebula with fusion reaction in the middle a protostar. Now we have a starting of a star. Now the star is born. As the kinetic energy increases, fusion starts to build up, and as more particles fuse together, the size of the nebula or the cloud keeps decreasing and is concentrated in the middle of the nebula, increasing the size of the star. Now, if the star is large, or the nebula has a very large mass, around the center part of the star, which is a protostar, there will be an accretion disk formed where the planets will be formed later on. So a small cloud only forms a protostar, and the protostar size keeps increasing. A very large nebula can create a protostar in the middle with an accretion disk around it, and the planets and moons and asteroids are formed in the accretion disk around the central part of the cloud. Now, as the mass of the star increases and the amount of fusion increases, eventually there will be enough heat to push outwards against the gravity. So we have two forces: the force of gravity pulling the particles inwards, and the pressure due to the heat from the fusion reaction pushing the particles outwards, expanding the gas. If these two forces are balanced, the size of the star becomes constant, and we call this star a stable star or a main sequence star. So what is the condition for a main sequence star to occur, or a stable star to occur or to take place? That the pull of gravity inwards is balanced by the output or the outwards push of pressure due to heat. Now, for a small sized star like our sun, the main fuel for the fusion reaction is the hydrogen gas, and the hydrogen gas keeps changing into helium. For larger stars, hydrogen turns into helium and then turns into heavier elements, but the main fuel is still hydrogen turning into helium, but then helium turns into carbon and heavier elements like oxygen and nitrogen and so on. If the helium is formed from all of the hydrogen inside the star, since all of the original fuel of the star ends or is used up, the star's temperature begins decreasing, so the core collapses and the outer surface expands because the gravity gets weaker and the temperature actually is cooler on the surface now, so it becomes red in color. For a small sized star, it becomes a red giant, and for a big star or a massive star, much more massive than than our sun, we call it as a red supergiant, which is much wider or much larger in diameter. So a small star creates a red giant, a large star or a massive star creates a red supergiant, and in this stage, red giant or red supergiant, fusion of heavier elements occurs. So helium turns into oxygen and nitrogen and carbon and so on, until all the fusion is used up. Now the pull of gravity will pull every particle inwards. While the pull inwards occurs, there is an area behind left called a planetary nebula. If the size of the star is small, in the center of the planetary nebula, the core of the star becomes a white dwarf. So for a small star, it started with a nebula, then it made a protostar, then it became a red giant, then it leaves behind a planetary nebula with a white dwarf in the middle. If there is a massive star, it starts as a large nebula, then a protostar. It could have an accretion disk, then a red supergiant when hydrogen is used up. When the all fusion is used up, it collapses again and creates a planetary nebula, but in the middle there will be an explosion called a supernova. So for a massive star, the collapsing causes an explosion called a supernova, and from the supernova at the center there is left either, for a small sized massive star, there will be a neutron star, or for a very massive star there will be a black hole, which is a very dense object with very heavy mass occupying a very small space, attracting all things surrounding. Even light cannot escape the black hole. So it is actually not a hole, it is a very massive object with a very high density. Now we go to something called the Doppler effect. The Doppler effect is the apparent change in observed frequency. So the observed frequency could be larger or less than the frequency of the source. If the received frequency is less, that means that the object is moving away from the observer. If the observed frequency is greater than the frequency of the source, this means that the object is moving towards the observer. So if the wavelength increases, that means that the object is moving away. If the wavelength decreases, this means that the object is moving towards the observer. If we are looking at objects that are a far distance away from us, for example, we are observing a galaxy that is a long distance away from our solar system, we observe the light coming from that galaxy redshifted, which means with a larger wavelength if the galaxy is moving away from us, or blue shifted, which means that the wavelength is shorter if the galaxy is moving towards us. But most of the objects, interstellar objects that we observe from Earth, appear to be red shifted, which means the light is shifted towards the red side of the electromagnetic spectrum or the visible spectrum. This means that this star or this object is moving away from us. So if you're required to explain what is redshift, it means the apparent increase in wavelength due to a source of light moving away from Earth. Okay, when we observe all the objects around the Earth, most of them are moving away. Actually, you can approximate it to all of the objects are moving away from the Earth, so they must be also moving away from each other. Another thing about redshift is something called cosmic microwave background. What is cosmic microwave background? That is background that is received at the Earth from all directions in the universe. So this microwave background must have been emitted a long time ago, since the distances in space are very large. So this goes back to the time of the beginning of the universe. But at the beginning of the universe, there was heat, a very large amount of heat, which is infrared radiation. But to go from infrared to microwaves, this means that the wavelength increased. So according to the Doppler effect, this is redshifted. So the wavelength increased, but by much larger amounts compared to what we see from Earth in visible light. So this microwave background radiation was emitted at the beginning of the universe or at the start of the universe from the explosions of the stars or the heat released from the stars as infrared. But infrared was redshifted towards the microwaves, which means that these objects are all moving away from us. This is another proof that all objects are moving away from us and from each other. So a scientist called Hubble comprised a graph of all the relative speeds of objects moving away from us. So if an object is moving away from us with a speed v, it has a distance d, and he plotted a graph of distance against velocity on y-axis, distance on x-axis. It was an approximate straight line that goes through the origin, so the speed is directly proportional to the distance. which means that the speed is equal to a constant multiplied by the distance, which he called it, according to his name, a Hubble constant. So the Hubble constant is the proportionality or the ratio between the relative speed of an object moving away from the Earth to the distance of the object from the Earth. And we have the unit here is meters per second, and the unit at the bottom is meters. So meters cancels meters, and we are left with 1 over second, or second to the power of -1. So this is the first part of the Hubble's law. The Hubble's law states that the relative speed of an object moving away from Earth is directly proportional to the distance of the object from Earth. So if you have a distance r and velocity v, if you have a distance 2r, then the velocity is 2v from the Earth. Now there is another thing, that all objects emitting light appear to have redshift in their light, which means all objects are moving away. So if all objects are moving away from each other, they must have started very close to each other at the beginning, which we call the Big Bang theory. Going back in time, if all objects are moving away from each other now, they must have been very close to each other before and must have started from a central point and then exploded or expanded. This is what we call the Big Bang theory. And using this theory, we can calculate the age of the universe going back in time to the Big Bang. We can calculate the age of the universe, which we call capital T. It is equal to 1 over the Hubble constant, and the Hubble constant is 2.2 times 10 to the power of -18, second to the power of -1. So we divide 1 over this, we get approximately 4.5 times 10 to the power of 17 seconds, which is approximately 14.4 billion years. And you can convert from seconds to years by dividing by 365, then by 24 and 60 and 60 minutes and seconds. So this was the end of the syllabus. I hope these videos were useful to you, and I wish you all the best in the coming exams.